Oh, do you want to learn math? Hang on one second. Oh, good. 97.5. You're all right. So let's get started. So we're on 10.2. So thus far we have learned some properties of logs, we've learned definitions of logs, and we've been learning a lot about exponential equations. So now let's solve them, shall we? So again, this is 10.2, and our Spark Our Learning piano has 88 keys. Each key is tuned to a specific frequency of sound waves in order to produce a unique musical note. From left to right, the keys produce notes that increase in frequency. Ow. So what mathematical question can you ask about this situation? So we've got frequency of note being played, position of the key, what is their relationship? I would personally like to know frequency versus tone and or note, but that might be outside of this specific problem. But I'm sure there's a relationship, right? So as we scroll down, now they don't give us that. But you can make a relationship with the frequency of notes being played versus the position, and I believe it has to do with an exponential function. So we need to know how to solve it, right? So let's go. So the first method for solving our exponential equations is basically the glorified calculator method. Other than just shoving the actual equation into the calculator, let's say we didn't have the ability to get a precise whatever, we can use the calculator function to narrow down and or estimate the actual value of the equation. So our calculators, so even our graphing calculators, so we can graph this, but that's not really solving it. We want to know when the output is 1,000. So, and let's say you didn't have a graphing calculator, maybe you only had a scientific calculator, so you could only do like the number stuff. So you can still kind of solve this and figure out when this thing equals 1,000. And the way you would do that is, let's pull our calculator out. So the first way, you can just enter the equation into this area right here over and over again. What I'm going to do is I'm actually going to use the table though. So you can always look at a table here, and that's going to be based on your y equals. So what I'm going to do is I'm going to enter the formula that they gave us, and that was 250 times 1.02 raised to the power of 3x. So then we can go over to our table, and remember, we want to figure out when that thing equals 1,000. So my table automatically generates a bunch of values. If yours does not, that's okay, because I actually wouldn't use these values. And if you were to, let's say, look in the book, they have a chart, and they go up by 5s, because that would kind of make a little bit more sense. Just because, okay, if 2 only gave me 200, 3 only gave me 290, we can probably skip a couple values in there, right? So let's see here. So my calculator is set up to where it automatically generates these, so I can't change them right now. It doesn't matter because I can just scroll down. So again, we want to know when it hits 1,000, right? So at 23, it's 980. At 24, it's 1,000. It's 1,040. So it's pretty close to 24. So we can solve it that way. Too easy, right? Let's get this out of the way. I'm going to write down that number 24. So I guess I should say f of 24 equals 1040.3. So then we have estimated the values of, choose the equation that represents this problem. So 1000 equals the equation they gave us. To estimate solution, start with convenient values of x. And what that's saying is, again, they've got a chart here, and they started with 5s, and they just went up by 5 increments so that they got to around 1000. So when they got here, they have 25 is above 1000, 20 is below 1000. So then they picked 23 and 24 until they got close. So basically, this is glorified guess and check, but be smart when you're guessing. So you don't have to go through every single one, especially if you're typing it in. So examine the columns in each row. How does the entry in the center column of the row lead to the entry in the last column and ultimately to the choice of a value of x for the next row? So basically, when you pick these values, this is what it's telling you. This is kind of technically probably what's happening in your brain. It's not something that I would generally write down, but this is what's happening. So they wanted to explicitly state that. So let's see here. The given function is an exponential growth because it's getting bigger. Function 1.02 is greater than 1, so the value of the function consisting is increasing. Therefore, the value of the function given in the center column is less than 1000. The next guess for x should be greater than the current value. Okay. The value in the center column is less than, the value in the center column is less than 1000, is greater than 1000, that's what I was looking for. The next value of x should be less than the current value. So again, this is the process that we kind of went through, just being put into words here. How can you use a table of values to determine the nearest whole number? Look at the values and then find the nearest whole number. The nearest whole number to the solution is, I was going to put in that number, 24. Okay, they want 23 then. The way that you can solve these equations, and this is kind of my preferred way, like if I couldn't solve it algebraically, I would probably default to solving something graphically. Because we have these super fancy graphing calculators, why not use them? So you can solve these things graphically by graphing the functions, but understanding what they're asking for, and then using the calculator to figure it out. So let's see here, what do we got here? So we've got the equation, then the graph equation shows two solutions. Okay, we've done that. So this is kind of a review of what we've done using graphing. So let's do it with our exponential function here. So with our graphing calculator, we are again going to type in our equation. So we've got solved the equation 6000 equals all of this, and let's say I have no idea how to solve that, but what this is saying is we've got an equation over here, and when does it cross the y equals 6000 line? So we're going to enter this equation in, and then we're going to enter a y equals 6000 and figure out where they cross. So that's the goal. So let's see here. Y equals 8,000.095. Oh no, that's what I get for trying to use the keyboard. 8,000 times 0.95 raised to the power of x. And again, we want to figure out when that thing equals 6,000, so we're going to make a y equals 6,000 graph. Now this calculator is way cooler than my graph because it's got pretty colors. So before we push graph, because I mean we can, I don't even know if we're going to see anything. See, so that's not useful. Let's look at our window and let's kind of think about things. So our first number here is 8,000. So when x equals 0, aka when it crosses the y-axis, that's going to be 8,000. So for our y, I don't think we necessarily need any negatives per se. Well, no, we might. Well, no, yeah, we probably won't need negatives, but let's still stick with 0. And let's say our y max is, I'm just going to say 8,000. So usually I go above the max, but we already know that it is a exponential, not growth, decomposition, or it's going to be going down. So that's why I'm picking that. So then our x minimum can probably be 0. I don't really know off the top of my head, so we're just going to try 20 and see where that gets us, and let's graph that. Hey, so exponential decay, that's the word I was looking for. So we knew it was an exponential decay, so I knew that we could start, it's going to start up here and go down, but we're looking for this point right here. So again, to make our calculator do that, we can go to calculate, and we want to find the intersection point. So our first curve is our blue curve, our second curve is our red curve. So the intersection is at x equals 5.6, we'll say 5.61. So I'm going to write that down, 5.61. So what two functions will be graphed on a graph calculator together? That one and that one, kind of what we talked about. What? Oh. Yeah, it might help if I read the actual equation. So that needs to be an x. My bad. What will the graphs of the two functions look like? So we've already looked at it, so I'm just going to go ahead and skip this problem. So here's our first curve that you saw on my graphing calculator. And then we have a line that goes at y equals 6,000. So find 6,000 on the vertical axis and move horizontally to the right along the grid lines until you reach the curve. Then move vertically down the grid lines that leads to the x-axis. Estimate the x value of this location using the scale. So again, we made our calculator do all that for us, but if you didn't have that intersect function, if you were doing it manually, you would follow this line over and then follow this line all the way down. Very few times will you be able to graph this curve on a piece of technology and not be able to find an intersection point at a certain line. So again, we've already seen it on our graphing calculator. So the graphing calculator, to identify the point in the intersection, what are the coordinates of this point? Round to the nearest hundredth, which I did. if necessary. So our x was 5.61 and our y was 6,000. Yay! And there's our graph. My all-time favorite way of solving exponential equations is, of course, going to be algebra, because I'm an algebra teacher. So our third way of doing it is solving these exponential equations algebraically. Basically, what you're trying to do is get both sides of the equation to be equal to the same base raised to a power, and then you can say something like that. So if b is not equal to 1, x and y, for all real numbers, b raised to the power of x is equal to b raised to the power of y, if and only if x is equal to y. So again, basically, you're going to try to get both sides of the equation equal to the same base, b, and then you can set the exponents equal to each other. So I think we've seen these before, and I also don't think it's like quite earth-shattering math or anything like that. So I don't think it's too bad. So we can do an example. So we've got this equation right here. Step 1, we're going to divide both sides by 3 just to make things a little bit easier. So we're going to have 2 to the power of x plus 3 is equal to 32. Ha! I was able to do that in my head. So now, this 32 can be expressed as an exponent 2 raised to the power of something. So I know that as number 1, it's even. That's not a surefire thing, but it's at least a multiple of 1, 2. So, and since I don't know this off the top of my head, we're going to hit the calculator. So we've got 32 divided by 2. That's 1. Divided by 2. That's 2. Divided by 2. That's 3. Divided by 2. That's 4. And then my last 2 is 5. So I can check that 2 to the power of 5 is equal to 32. So we can rewrite our equation as 2 to the power of x plus 3 equals 2 to the power of 5. Now that we have that, we can say x plus 3 is equal to 5, and then this is basic algebra, x equals 2. Oh look, that's the same thing they got. So what reasons justify the last 2 steps of the equation? I would say property of equality for exponential equations, because that's what we just learned. Oh, and then subtraction property of equality. So why is the first step of the solution process division by 3? So we have this 3 here that's kind of in the way. We need to get this exponent all by itself before we can do this new exponential equality type stuff. So sometimes the algebraic way, you can't get both sides equal to the same base, and so you might have to use logarithms to be able to solve it algebraically. So we can do that. So this says solve the equation, all of that. So we're going to do some basic algebra. We're going to get this guy by itself first. So we're going to add 7 to both sides, and then we're going to divide by 5. And I'm just going to put that in my calculator. So 43 plus 7 divided by 5 So now we have 3 raised to the power of x equals 10. So now we've got actually a pretty simple quote-unquote log problem. Using the definition of log, we can say, we can do log base 3 of 10 equals x. So again, that's our definition of log that we've used. Or if you want to think about, no, I'm not gonna say that. That'll confuse us. But a normal calculator, and I know some of you have to do fancy calculators that can do this, but a normal calculator can't really deal with this log base 3. So we can use our properties of logs to switch that over to a log base 10 that our calculators can then handle. So the way we would do that, based on those properties, is this part would change to log of 10 over log of 3. So that is a property of logarithms. And remember, since there's no number there, that's insinuated log base 10, or common log. And so all of that's going to be equal to x. So your 10 is on top, your base is on bottom. So this is something that can be plugged into your average scientific calculator. So if we pull that up, so it's just going to be log of 10, which equals 1, divided by log of 3. And so we are going to get 2.096, which is what they got. So why can't the property of equality of exponential equations be used at the point where the equation is that? So we cannot express 10 as an easy power with a base 3. So we just can't do that easily. So since 10 is not the power of 3, the two sides of the equation cannot be written using the same base. What property justifies this one? It was the change of base property or something like that. We gotta have a real world problem, right? And look at that cute little puppy. Not really. Small dogs are weird. They scare me. So real world problems modeled by exponential equations. You can use algebra to solve real-world problems. For example, the amount of medicine that remains in a body decreases exponentially over time as the body processes the medication. So the amount of medication remaining in a person or animal's bloodstream at any given time since the medication was administered is modeled by an exponential decay function. In this case, we're using this one right there. During the annual checkup, a veterinarian diagnosed arthritis in the hips of Marissa's dog. Veterinarian instructs Marissa to give her dog 1 300 milligram tablet of medicine per day to treat the arthritis, and then administers the first tablet. The amount of medicine A remaining in the dog's bloodstream after T minutes can be expressed by an exponential decay function. How long will it take the amount of medicine to drop to 75 milligrams? So this is the equation they gave us. After we plug in 75, we get right here. So now we need to solve this. So we've got 75 equals 300, 1/2 raised to the power of t over 15. So just like we did before, we're going to start by doing some simple algebra, divide by 300. So 75 divided by 300, 0.25. So let's keep that in a fraction for now, just because we already have one fraction over here, so that might be helpful. So 1/4 is equal to 1/2 t to the 15. So at this point, I'm hoping that you recognize that 1/2 and 1/4 are similar. So we can express 1/4 as 1/2 squared, right? So now we have 1/2 to the power of 2 equals 1/2 t over 15. And again, because of our exponential equality rule, or whichever property, or whatever the formal name of that was, we can say 2 is equal to t over 15. Then we just do normal algebra, 15 times 15 by both sides, we've got 30 equals t. So the answer is going to then be 30 minutes. So t equals 30. So what has been done in step 4 of the solution? What alternative way could this have been done? Left side of the equation was rewritten as a power of 1/2, matching the base, the exponential side on the other side. Or we could have, both sides of the equation could have been rewritten as powers of 2, and then use negative exponents. Sure, why not? It's not a thing I would have done, but wouldn't have been wrong. What is the justification? The thing that we have already learned. Property of equality for exponential equations. So it will take 30 minutes for the amount of medicine to drop to 75 milligrams. And especially when we have multiple ways of solving an equation, if you ever want to double check yourself, graph it. So here's a graph of our equation, and then they just entered y equals 75. And you can see that it crosses right at 30. You can also use your calculator to do the intercept, and it would tell you that coordinate would be like, what was it, 30, 75. The point of intersection of the graph is, what did I just say? 30, 75. So the coordinate t matches the value found algebraically. Yay!